So here we're beginning section 1.3, which is about primes, and eventually we're going to get up to the fundamental theorem of arithmetic, which talks about how every integer that's not 0, that's not 1, that's not -1 can be written as a unique product of primes, or we can say it has a unique prime factorization. So this is our section on primes. So we're going to begin with the definition. What is a prime? So in number theory, you normally say that a prime is a positive integer greater than 1 whose only divisors or factors are 1 in itself. We're going to define a prime differently. We're going to allow for negative primes. So we're not going to just talk about positive primes greater than 1. We're going to talk about negative primes as well. So we're going to say definition. An integer p is said to be prime provided three things happen. Number one, p can't be 0. That's the first thing. Number two, p cannot be either 1 or -1. So p is not plus or minus 1. And number three, the only divisors of p are plus or minus 1 and plus or minus p. The only divisors of p are plus or minus 1 and plus or minus p. So there are basically three things here we need to pay attention to. P is not 0, p is not plus or minus 1, and then its only divisors are plus or minus 1, plus or minus p. Okay, so here's our first fact. I'll call this fact 1 for this section. Fact 1 for section 1.3. If p and q are both prime, now p and q are typical letters that you would use for primes. P and q show up a lot. When you're dealing with primes, you want to use those letters for primes. When you are out of q, maybe you go to r, and then maybe s. But right now we're going to use p and q. P and q, let's say p and q are prime, and p divides q. So in other words, if one prime divides another, then that means p must be plus or minus q. So I want to prove an if-then statement here. So I want to prove this. So to prove an if-then statement, we're going to assume the antecedent here in blue. So let's suppose p and q are both prime. And also p divides q. Okay, so remember q is prime. Q is prime. So since q is prime, we know q is not 0. We know q is not plus or minus 1. But also we know the only divisors of q are plus or minus 1 and plus or minus q. And the only divisors of q are plus or minus 1 and plus or minus q. Those are the only divisors of q. Plus or minus 1, plus or minus q. Now note, p is a divisor of q, since p is a divisor of q, right? That's part of our hypothesis that we're assuming. P and q are prime, p divides q, so p is a divisor of q. Since p is a divisor of q, then what does that mean? That means p is either plus or minus 1, or p must be plus or minus q. That's because the only divisors of q are plus or minus 1 and plus or minus q. So it means p must be plus or minus 1 and plus or minus q. Now we can rule out one of these cases. P cannot be plus or minus 1. Why? Because p is prime. Note that p cannot be plus or minus 1 since p is prime. Okay, Okay, so basically we rule out this case. That just leaves the case where P is plus or minus Q. So therefore, P is necessarily plus or minus Q, and that's it, right? We arrived at this consequence here. That's the proof. Put a little box here. Okay, it's not supposed to go like that. Okay, I don't want to draw with my finger. I want to shift. There we go. So if one prime divides the other, then that means that prime is either a positive of itself or it's a negative of itself. So for example, if I have a prime dividing 3, then that prime P must be either 3 or negative 3. That's it. Common sense. All right, here's an exercise. Throw this in there. Here's a good exercise. So this is a really nice exercise. I don't know if this shows up in your homework, but it's a really good exercise. Really good one. So put a star near this one, because you may see this one on your exam. Show if P greater than 3, I didn't write greater than very well, greater than, hey, it's not writing well. If P greater than 3, what happened to my pen? There it is prime. So let's say I have a prime that's bigger than 3. Then that means that P squared plus 2 is not prime. Necessarily not prime. So I have an if-then statement I want to prove. So I'm going to assume the antecedent, that's P is greater than 3, and it's prime, so proof. Suppose P greater than 3 is prime. What I'm going to do, I'm going to do the division algorithm between P and 3. I'm going to say by the division algorithm. That's going to continue to show up throughout the semester. It's always useful. So I'm going to use P, and I want to divide 3 into it. So I can write P as 3 times Q plus R. So with Q and R integers, and R is going to be between what? Greater than or equal to 0, less than 3. That's the division algorithm. So we're doing the division algorithm dividing 3 into P. So basically we have 3 cases to consider when you have a remainder of 0, remainder of 1, and a remainder of 2. So here's case 1. What happens when you have a remainder of 0? So let's suppose the remainder here is in fact 0. Well, we're going to actually show this can happen. We're going to show this can happen. That would mean if R is 0, that means then P is equal to 3Q, right? If I plug in 0 for R, I get 3Q. So that means 3 divides P, right? 3 divides P. P is a multiple of 3, so 3 divides P. But by our fact, remember we just had a fact, if a prime divides a prime, then the dividing prime must be plus or minus the other prime. So that means that 3 equals plus or minus P. It's according to our fact 1 by fact 1. But that can't happen, right? Because we know that back here, P is greater than 3, right? P is greater than 3, which is a contradiction. Since P is bigger than 3. Okay. So this case you can completely rule out. Now the other 2 cases we're not going to rule out. The other 2 cases we're actually going to work through. So case 2. So basically this first case, I put it in red because we're going to rule it out. The other 2 cases we're going to show that they give that P squared plus 2 is not prime, the second in the third case. So the second case would be when you have a remainder of 1. Suppose you have a remainder of 1 when you're doing the division algorithm between p and 3. Then that means p is of the form 3q plus 1. Okay? Now what I'm going to do, I'm going to take, I want to get this equation here, or this expression, p squared plus 2. P squared plus 2. I'm basically going to take p, I'm going to square it and add 2. So that means p squared plus 2 is, well, in place of p here, I'm going to put 3q plus 1. I'm going to square that. Let's see, when I square 3q plus 1, I'm going to get 9q squared plus 6q plus 1. And then we add a plus 1 on the end. That's going to give us, oh, plus 2. That should be a 2 on the end. What am I doing? Plus 2. Okay, so we're going to simplify this. This is 9q squared plus 6q plus, so I'm going to add the 1 and the 2 here. I'm going to get 3. And this is equivalent to p squared plus 2 equals, I'm going to factor out a 3, right? I'm going to factor a 3 out of here, here, and here. It's going to give me 3 times 3q squared plus 2q plus 1. Okay, so that means, 3 divides p squared plus 2, right? That's what that means. Now, if 3 divides p squared plus 2, is it possible for p squared plus 2 to be prime? No. No. Remember, the only divisors of a prime are 1 in itself. And 3 is not p squared plus 2, right? It's much smaller than p squared plus 2, because p squared plus 2 is bigger than 3 for sure. So note that p squared plus 2 is not prime, since p squared plus 2 how do I want to say this? Is not plus or minus 3. Yeah. You could say it that way. I'll just say since p squared plus 2 is bigger than 3. Yeah, p squared plus 2 is bigger than 3. Okay, so the only way that p squared plus 2 could be prime is if p squared plus 2 were 3 here, right? If it were 3. If 3 divides p squared plus 2, then p squared plus 2 would have to be 3 in this case. But it's not, it's bigger. Okay, let's do a case 2. Case 2, we want to look at the case when the remainder is 2, right? We've done remainder 0, which was a contradictory case. We basically ruled that case out. Case 2 led us to the fact that p squared plus 2 is not prime. Let's do that once again, but this time with r equal to 2. Let's suppose r equals 2. And that means p is of the form 3q plus 2. That's when you have a remainder of 2. So when I look at p squared plus 2 again, this time I'm going to plug in 3q plus 2 for p. So I'm going to have 3q plus 2, quantity squared, plus 2. It's going to FOIL out to be 9q squared plus 12q plus 4 plus 2. And when I combine my like terms here, I'm going to get a 6 there. So I get 9q squared plus 12q plus 6. That's equivalent to p squared plus 2. So factor out a 3 out of all of these. When I factor out a 3, I'm going to get 3q squared plus 4q plus 2. So that means, what happened? So that means 3 divides p squared plus 2, once again. And that means that p squared plus 2 is prime. Why is p squared plus 2? Sorry, not prime. Is not prime, I should say. Because the only divisors of prime are itself and 1 when you're dealing with positives. We know p squared plus 2 is obviously positive. So its only divisors can be 1 in itself. And 3 is not 1. And 3 is not the same thing as p squared plus 2 because p squared plus 2 is bigger than 1. So I'll just say since p squared plus 2 is bigger than 3, I should say, bigger than 3. All right, so that proves it. We've done case 1 got ruled out. Case 2 and case 3 both showed that p squared plus 2 is not prime. And that's what we wanted to arrive at, right? We wanted to arrive at that p squared plus 2 is not prime. That's a really good exercise. I think that's one you should learn how to do, even if it's maybe not on your homework.